Bismillahirrahmanirrahim. Dear student, in today's lecture I am going to tell you about the three topics of the digital logic design. The first topic what I am going to explain is the logic, and the second topic is the use of logics in gates, and the third topic what I will explain in today's lecture is the correlation of logic gates with switches. So first of all, let me explain you the concept of the logic. As we have talked about this topic in my previous lecture as well. So logic is what? Logic is intelligence. By intelligence we mean the power of mind. If a person is more logical, so it means that he is more intelligent. And if a person is more intelligent, so that person is having good power of mind. And what is the outcome of the power of mind? The outcome of the power of mind should be the optimum results or the better decision. A logical mind can always gives you the right decision or the optimum results. So now how we can get the optimum or the right decisions? It based on the reasoning. Every problem have certain reasoning. Once we take those reasons into account, then we decide based on those reasoning. Sometimes reasonings are too heavy or too much reasoning are there in certain problems, that we see that the reasonings may have some conflicting requirement. So sometimes it is difficult for some minds which are not that much logical, not that much intelligent. So it is why there is a solution for that problem. Mean in today's world, in this technological world, the machine has taken this job from the humans, from the general humans. Yes, of course, there are some powerful minds which specially design these machines. But if we have to resolve some logical issues, so we put those logical issues into a machines or an electronic gadget, and then electronic gadget resolve that issue for the people, for especially I must say for the common people. So here mean first, but we have to understand that what is meant by logic. So let me explain you formally that logic creates reasoning, and based on the reasoning we come up with the optimum solutions. Optimum solutions of the problems. These problems may be of any type, maybe problems of the society, maybe problems in machines, maybe problem in certain gadgets, and there are much more examples. But logic can give you right decision or optimum solutions. And between the logic and optimum solution, we get involves the reasoning. Based on reasoning, we get the optimum solution. Now let me give you an example. Look at this example. What is written in this statement? This statement says that if a student study the right topics, he or she will be able to get good grades. Now this is a very simple type of the logical statement. In this statement, we have some logic, and logic is that if a student study, this is one reason, and second reason is if he or she is studying but the right topics. Actually the right topics is also a reason. Then if these two reasons get fulfilled, then what will be the outcome? What will be the optimum result, optimum solution of this problem? The optimum solution or result of this problem will be good grades. Now here you can see that if a student study, but if he studied some irrelevant topics, so he or she will not be able to get good grades. So here means the two reasons or the two condition must be get satisfied in order to get the outcome. What is the good grade? What is called the good grades? So now if I put this logical statement into a logic circuit, so for this logical statement I required an AND gate, because this AND gate will get these two conditions or reasons, and based on these two reasons it will create the result for the common people, for the general people. Now this is a very simple example, but we may have a very complicated or sophisticated type of logical issues. So for that purpose we have to use a bigger circuit, but right now this is a simple statement having two reasons or two conditions and one output. So in this case we may use one AND gate, because in one AND gate with two inputs. Now the two inputs are the two reasons, are the two conditions for that issue. An issue is the getting the good grades. Now good grades will be produced as per the input conditions, and what will decide the good grade? It will be decided by the logic circuit right now. We will not manually give the output, the result. Automatically this logic circuit will produce the result. First it will look into the input conditions. So now, being a digital designer, we will decide that if study is 1, it means that that particular student is studying. But if study is 0, it means that particular student is not studying. He knows the right topics, but he is not going for the study. Let's say he knows the right topics, but he is not studying. Studying is equal to 0. What will be the output? 0. It means the student will not be able to achieve the good grades. Now, what if we say the student is studying, but he is not studying the right topics, mean he is studying some irrelevant topics. So what will be the outcome? Not good grades. Because one of the two conditions is false. When the two input conditions are true, so what will be the outcome? The outcome will be the good grades, and that is true as well. That is 1. So now what I am trying to tell you is that if we have the problems like this, problem statement like this, we can model those problem statement into a logic gates, logic circuits. And this is one of the simple examples that what you can see right now. Now let me talk about the second example. There is a logical statement. What is the statement? Let me read out the statement for you people. You may manage good grades if you are intelligent enough or hard worker. Now if you look at this statement, there are two conditions in order to get good grades, but the two conditions are having or in between. It means some intelligent students, if they are not even hard worker, but they are intelligent student, and if they do smart work, not the hard work, they will be able to get good grades. And if there are students who are not that much intelligent, but they are very hard worker, so by consistent efforts, they may also get good grades. So now in this statement, what you can see, if we have to put this statement into a logic circuit, we are required to implement the OR gate instead of the AND gate. Now here, OR gate means the two input conditions are this, intelligent enough and hard worker. If any one of these condition is true, let's say intelligent enough is 1, he is not hard worker but smart worker, the result will be good grades. And if other way around, mean if he is not that much intelligent but he is a hard worker, so with the consistent work, he or she may also get good grades. And if both are there, so of course means still that student will be able to get good grades. So now what I am trying to explain you is that if you have a logical statement like this, a logical problems like this, and in that logical problem you can see the reasoning in that, reasonings are the inputs, and the optimum solution is the output of that reasoning. So we can implement that by using the logic gates as well. Now let me give you the third example for the third basic logic gate, and that is NOT gate. Now let me read out the statement first. You can take a high jump by pressing down your feet on the ground. So now look at the statement. One is the output, which is the high jump. Another is the input, which is pressing down the feet on the ground forcefully, or with more force. So if you are pressing down, you will be able to get more height. So this is another type of logical statement, and there is reason and there is the outcome. So we can implement this reasoning by a NOT gate. Pressing down mean if it is 1, so mean we are forcibly pressing down the feet on the ground, we will get the high jump. But if you are not pressing down the feet on the ground forcefully or with the more force, we will not be able to get high jump. So in that case, if we are pressing the ground, so here you can see that, let's say we are pressing down, and if we are going more down, we will be able to get high jump. If we are not going down, we are not pressing the feet down, it means in that case the input is 1, not pressing down much. So what is the output? You will not be able to get the high jump. So these are few examples. What I am trying to explain you, that how can you relate the problem statements with the logic gates. And you know that in the logical world we are having these 3 gates only, and these 3 gates have given you the examples that how can you model the logical problems into a logic circuits. Now here one point more I love to explain, and that is that in a statement there might be more reasoning instead of only 2 reasons. Might be there are 10 reasons, there are 12 reasons, or there are 4 reasons or 3 reasons. Maybe the reason will be more than 2. Then you will use the more input AND gate or more input OR gate. But of course for NOT gate we will have 1 input and 1 output. So it will basically strongly relate to certain condition where we have 1 input and 1 output. So now one more point is that gates may have multiple inputs, because reasons may be multiple for certain problem. If reasons are multiple for certain problem, so we may have a more input basic gate as well. That may be OR gate, that may be AND gate, that may be some other derived gate. But we have these type of modeling. And why we need to model, as I already explained you, that if we have a problem or logical problems, and if we model these logical problems into a logic circuits, then the logic circuits are very rich in terms of different types of the mathematical models. So we can resolve the logical problems in a very simple way. So it is why we have to put those logical reasoning into a logic circuit. Now third point what I am going to explain you in this lecture is, let me just wipe it out so that I can explain the last topic of today's lecture. Now this one, correlation of logic gates with the switches. Let me explain you that, let's say I have 2 switches connected in series, and here is a bulb. Let's say this bulb is a DC bulb and it requires some 12 volt DC voltage. So this is positive, this is negative. So this is 12 volts. Now there are 2 switches. Now here you can see that the 2 switches, suppose I name these 2 switches by, suppose this switch is switch X and this switch is switch Y. So the state of the switch may be either open or close. If X is equal to 0, so it means switch is open. If X is equal to 1, so it means the switch is closed. And same is the case for the second switch as well. If Y is equal to 0, so it means that switch is open. If Y is equal to 1, it means switch is closed. Now here you can see that if you close both the switches, then you will be able to turn on the bulb. Otherwise you will not be able to turn on the bulb. So what does this type of switch arrangement represent? This type of switch arrangement represent the AND gate. It is having 2 inputs X and Y, and there is 1 output, and that is bulb. Now if both switches are 1, bulb will get 1, bulb will turn on. B is equal to 1 means bulb will turn on. If any of these two input is 0, bulb will not get turned on because the two switches are connected in series. So this is the first example that we can correlate the arrangement of switches with the logic gate. Let me talk about the second type of circuit. And let's say the second type of circuit is the two switches connected in parallel, not in series. The two switches are connected in parallel. So here you can see that, let's say the two switches are connected in parallel, and here is the bulb. Let me say, and again this is a DC bulb which requires a 12 volt DC supply. This is positive, this is negative, 12 volt DC supply. Suppose I label this switch by X and I label this switch by Y. So now if any of these two switches is closed, suppose X is equal to 1 and it is open, Y is equal to 0, the bulb will turn on because this supply source will get this path and the bulb will turn on. What if we keep this switch open and the second switch closed? Now this supply will get this path and the bulb will turn on. So it resembles just like an OR gate with two input X and Y, and this is B. If any of these two input is 1, bulb will turn on. This case, or maybe this case, this bulb will turn on. So these two switches connected in parallel resembles just like an OR gate. So it works just like an OR gate. Now let me talk about the third basic gate, which is the NOT gate. Let me explain that as well. Now, suppose we have a push button. Push button is the button which remains normally closed. And here is the bulb. Bulb is connected here. Same example here again. A bulb is a 12 volt DC bulb. So now this is, suppose I represent this switch by X. Now X may have two values. It is equal to 0 mean if there is no force is exerted on this push button. If no force is exerted, so it is normally closed. Normally closed mean the connection is intact and this supply is available to bulb and bulb is turned on. And second mean X may have the value 1 as well. 1 mean external force is now exerted. When the external force will exert it, so it is mean a spring is there in the push button and this circuit will get open. When this circuit will get open, now the supply will not get the path in order to turn on the bulb. Now bulb is 0. So this X represents the presence or the absence of the external force on this switch. So this resembles just like a NOT gate. So now in this lecture I have explained you about the logic, the use of logic in the gates, the correlation of the logic gates with the switches. So this is all for today's lecture. In today's lecture I have talked about these three topics. As I mentioned you in my previous videos as well, that if you required any topic that I should give a lecture on, so better you should write me in my comment in my YouTube channel, and I would request all of you that please subscribe my YouTube channel and share with your friends. All the best. Take care of yourself. Allah Hafiz.